We all think of Einstein's general relativity as this perfect, untouchable pillar of science. And it is. It's one of the most successful theories ever. But what if I told you it has these huge fundamental holes right at its core? That's what we're going to dig into today, the biggest unanswered questions at the very heart of Einstein's greatest idea. Okay, so you've probably heard this quote before, right? It's the elegant one-liner that sums up the whole theory. I mean, it's beautiful. The core idea that matter and energy aren't just passive things floating around in space. Nope, they're actively shaping it. And that shape, that curvature, is what we experience as gravity. It's a stunning concept, and it just plain works. So yeah, let's start with what made Einstein's idea so revolutionary in the first place, and how he totally reimagined what gravity even is. Think about it. Before Einstein, we had Newton. And Newton's idea of gravity was basically, well, a mysterious force, right? An invisible string pulling things together. But he could never explain how that pull worked across the vast emptiness of space. Then Einstein comes along and provides the mechanism. He says, forget the mysterious pull. Instead, picture this. A massive object like our sun literally bends and warps the fabric of space-time around it. And planets, like Earth, we're not being pulled, we're just rolling along the curves in that fabric. He answered the how. But here's the twist. For all its brilliance, Einstein's theory is kind of missing some machinery. It's an absolute masterpiece at describing how gravity works, but it's strangely quiet on the fundamental why. And this right here is the central question his theory just doesn't address. His entire universe, everything he describes, is built on two pillars: space-time, which is the stage, and energy, which is the actor on that stage. But what are they? What are they actually made of at the most basic level? And here's the part that's kind of mind-blowing. The theory works. It works perfectly. But it does so without ever defining what its most basic ingredients are. It's like, imagine someone gives you the perfect recipe for a cake. It tells you exactly how to mix ingredient A and ingredient B to get a delicious result every single time, but it never ever tells you what those ingredients actually are. So let's break this down into the two big mysteries, okay? First up, let's talk about the stage itself. What is space-time really? Einstein gives us this incredible concept of space-time, this fabric of reality, but he never actually tells us what it's made of. Like, is it a thing, a physical substance? Does it have properties, like elasticity that let it bend and warp? And how does energy even sit inside of it? Does it push space-time out of the way? Or do they somehow occupy the same spot? We just don't know. The theory is completely silent on this. And now for the second big mystery, the actor performing on that stage. We're talking about the enigma of energy. And you guessed it, it's the exact same problem all over again. What is energy at its most fundamental level? Why does this stuff have this incredible, almost godlike power to warp the very fabric of reality? And, saying everything is made of energy sounds profound, but it doesn't actually solve the problem. It just raises the same questions. We still don't know what it is or how it's so intimately connected or coupled to space-time. So you're probably wondering, if Einstein didn't have answers to these huge questions, how on earth did he connect them in an equation? Well, this is where his genius really shines through. He came up with a brilliant mathematical workaround. He used a technique called geometrization. Now, that sounds complicated, but the idea is actually pretty straightforward. It just means taking a physical thing you don't fully understand, like energy, and finding a way to describe it using the pure language of geometry and math. If you can describe its behavior mathematically, you can work with it. So here's the magic trick. Einstein had a real problem. On one side of his equation, he's got the geometry of space-time. On the other side, he's got all the energy and matter. These are, physically different concepts. His solution was pure genius. He decided to represent both of them using the exact same mathematical object. It's something called a 4x4 tensor. Once they were both speaking the same mathematical language, he could finally build that bridge between them. He could finally legitimately put an equal sign right in the middle. And this just perfectly shows both the power and the limits of his achievement. This mathematical model is fantastically successful for big things, planets, stars, entire galaxies, but it's an incomplete picture. The theory just doesn't have the tools, the machinery, to describe the tiny, fundamental structures of reality where quantum mechanics is king. Which brings us to our final thought, the next frontier. Because these gaps we've been talking about, they aren't failures, not at all. They're clues hiding in plain sight, pointing us toward the next great revolution in physics. So, really, the best way to think about general relativity isn't as some finished final answer. It's more like an incredible roadmap to the universe, but a roadmap with some huge, important sections just blank. And the job of physicists today and tomorrow is to fill in those blanks, to finally tell us what space-time and energy are actually made of. And that's honestly what makes all of this so exciting. These unanswered questions, these gaps in the theory, they're not a dead end. They're an invitation. They are the breadcrumbs that are going to lead us to an even deeper, more complete understanding of our universe. So, what do you think those tiny structures might be made of? It's pretty much the biggest question physics has left to answer.